Why did the Dyson Sphere, judged by physicists for 60 years to be inherently unstable, suddenly get a theoretical lifeline in 2026? When physicist Freeman Dyson proposed the idea in 1960, the whole astronomy community was stunned by its sheer audacity. Once a civilization could command the energy of an entire star system, it would build a vast structure around its star and harvest all of its radiation. That was the signature technology of a Type II civilization. The Dyson Sphere then became a fixture of high-end civilizations in science fiction, and one of our key reference points in the search for intelligent alien life. But almost as soon as the idea appeared, the objections started. The killer objection was never can we build it, but can it stay stable? In the old celestial mechanics calculations, Dyson-like structures were unstable right from the start. Whether it was a rigid, complete shell or a Dyson bubble held up by light pressure, it met the same fate. Start with the best-known version, the rigid Dyson Sphere. Most people picture a perfectly sealed, giant shell enclosing the whole star. By Newton's shell theorem, a uniform shell exerts zero net gravity on the star inside, so it sounds like it could just hover there. But that zero net force is exactly the problem. It's an incredibly fragile balance. Give the shell even the tiniest disturbance, an asteroid impact, uneven mass inside it, even material ejected by the star, and the shell shifts relative to the star. Once that happens, the nearer side feels a sharply stronger pull, while the far side feels less. The balance collapses, and the shell falls into the star and is destroyed. In other words, a complete rigid Dyson Sphere is unstable by nature. However perfectly you build it, it won't last. So what if we step back and use a Dyson bubble instead? Come to its ultralight mirrors, with starlight pressure balancing gravity, like floating solar cells, not orbiting the star, just hanging quietly in place. A lot of people once liked this approach because it avoided the engineering nightmare of a rigid shell, but the traditional math was still pessimistic. When a single reflector is treated as a point mass, the balance between light pressure and gravity is an unstable equilibrium. What does that mean? Imagine placing a small ball on top of a smooth, larger ball. In theory, there's a balance point where it can sit still, but with the slightest nudge, it rolls off immediately and never comes back. A Dyson bubble has the same problem. If one deflector lifts even slightly from equilibrium, either light pressure meets gravity and it drifts farther and farther out, eventually leaving the system, or gravity wins and it falls into the star. To keep it stable, every reflector needs its own active propulsion and constant course directions. For billions of reflectors, the energy use and cost are astronomical. From an engineering standpoint, it just doesn't add up. And that view, that Dyson structures are inherently unstable, held for more than 60 years until January 2026, when University of Glasgow engineering scientist Colin McGuinness published a paper in Monthly Notices of the Royal Astronomical Society that quietly broke the consensus. His key move was actually very simple. Everyone had been calculating one thing wrong. These giant structures shouldn't be treated as point masses. In earlier calculations of gravity and light pressure, we assumed the structure was tiny compared with its distance from the star, so we could treat it as a point and apply the inverse square law. But Dyson structures are on a completely different scale, hundreds of millions of kilometers across, spanning an entire star's habitable zone. Their own size is the same order as their distance from the star. At that scale, gravity and the radiation pressure vary across the structure too much for a point mass model. The inverse square errors get magnified, and that very mismatch creates room for stability. Using a more accurate force model, the study showed that two Dyson-type designs can be completely passively stable, no active propulsion, no constant correction, and after a disturbance, they return to equilibrium on their own. The first is a ring-shaped stellar engine. Earlier stellar engines were usually imagined as one huge circular mirror facing the star, hovering on light pressure while using reflected starlight to push the star along. Under the point mass model, that disk is 100% unstable. But this study found that if you change the mass distribution, put most of the mass around the ring as a heavy, ring-shaped frame, and leave only an ultralight reflective film in the center, the whole structure becomes self-stabilizing. It works a bit like a roly-poly toy. When the structure shifts, the heavy rim creates a larger gravity difference. Together with the changed light pressure pattern, the net force pushes it back to equilibrium. This ring could harvest the stellar energy and serve as a stellar engine carrying the whole star system through space, with no extra power needed for balance. In theory, it could stay stable for billions of years. The second is a dense Dyson cloud. One light pressure reflector is still unstable. That conclusion still holds. But what if, instead of one, hundreds of billions of reflectors packed together into a dense cloud around the star? The study found that when the cloud is dense enough, light scattering between reflectors creates an internal confining effect. If the whole cloud shifts toward the star, the reflectors on the near side receive stronger radiation, and scattered light builds higher internal pressure that pushes the cloud back outward. If the cloud shifts outward, inner light pressure weakens, and overall gravity pulls it back. Put simply, a dense Dyson cloud behaves like an elastic gas. It can hold its own shape without giving every reflector a separate control system. That also changes how we think about Dyson clouds. People used to imagine them as sparse pieces, each following its own orbit. The stable form may actually be a dense, light-pressure cloud. Around the same time, another celestial mechanics study found a special route to stability for the classic rigid Dyson sphere. In a binary star system, if a rigid Dyson sphere encloses a smaller star and the mass ratio meets a critical condition, the smaller star is less than 1/10 the mass of the larger one. Then, under the restricted three-body problem, that sphere around the small star can orbit the larger star stably. Of course, the conditions are harsh, and it only works in certain binaries. Still, it leaves a sliver of theoretical possibility for the classic Dyson sphere. Now, let's clear up a few common misunderstandings. First, this absolutely does not mean humans can build a Dyson sphere now. All these results are still pure theoretical mechanics. They only show that physics does not forbid such structures from being stable. They say nothing about engineering feasibility. Dismantling entire planets for raw materials, creating materials that can withstand stellar-scale forces, and precisely arranging billions of components. Every one of those problems is far beyond our current technology. Human civilization hasn't even reached the threshold of Type 1. A Type 2 civilization that can build star-scale megastructures is at least tens of thousands of years ahead of us, maybe more. The gap between theoretically possible and practically buildable is an entire level of civilization. Second, there's no observational evidence that such structures already exist in the universe. The online claim that the Milky Way contains 7 suspected Dyson Sphere stars is basically clickbait exaggeration. Those unusual light curves all have more reasonable natural explanations. Blockage by interstellar dust disks, occasional overlap in multi-planet systems, stars' own magnetic activity and star spot changes. Until every natural possibility is ruled out, we cannot casually declare it an artificial structure. Our astronomical observations are still limited. We still understand many cosmic phenomena only shallowly. Blindly calling every anomaly an alien civilization is no different from ancient people blaming disasters on gods and spirits. Finally, this is not some earth-shattering breakthrough that overturns physics. It doesn't overthrow any fundamental law or discover a new principle. It simply corrects errors caused by earlier simplified models. Within the niche field of celestial mechanics, it adds a more precise result. Its value is mainly in engineering astrodynamics and the search for extraterrestrial civilizations, not rewriting physics textbooks. Of course, none of this means the research is pointless. Quite the opposite. Its real value is giving us a clearer direction in the search for intelligent life beyond Earth. For decades, when SETI projects looked for Dyson Sphere signatures, they mostly searched for the infrared access of a complete shell or for regular scattered dips in starlight. But now we know that a truly stable stellar-scale metastructure is probably not a solid shell at all. It is more likely a ring structure or a dense cloud, and those would produce completely different radiation patterns and light curves. With that theoretical guide, astronomers can adjust what they observe and how they filter the data, so they can target possible technological signals instead of wasting time in the wrong place. In fact, looking back at the Dyson Sphere's 60-year history, you can see humanity's imagination about the universe slowly being brought down to solid ground. At first, it was just a physicist's wild, very science fiction idea. Then, basic physics was used to test it, exposing its flaws and impossibilities. And now, final calculations have carved the boundary of possibility out of the impossible, finding forms that really obey the laws of physics. Human progress has always worked this way. First, imagination sketches some distant outline. Then, physics refine it bit by bit, stripping away what cannot stand and leaving what can. We are still nowhere near building something like a Dyson Sphere, and maybe we never will. But simply knowing that is already romantic enough.